Mr. Maynard is Laboratory Director of HFL Sports Sciences, where he has 20 years' experience in a variety of operational and management roles. His other professional interests include as a member of the Association of Official Racing Chemists, a member of the UK Anti-Doping Scientific Expert Group, a member of the London Toxicology Group, and he's a visiting reader in the School of Chemical Sciences and Pharmacy at the University of East Anglia. Mr. Maynard is going to speak this morning about laboratory costs of quantitative analysis.
Thank you, Ken. Your Royal Highness, ladies and gentlemen, good morning. Welcome to the final formal session. I'd like to thank the FEI for the invitation to speak to this Congress. I also must remember to ask Graham why I'm the only speaker that seems to be addressing cost as the very last lecture in the process. I had prepared a very short version of this in case we were running out of time, and the short version pretty much runs regulatory thresholds, need validated quantitative analysis, which increase laboratory costs. Fortunately, we do have about 15 minutes, so I will explain to you why that's the case. That's if I can get my head around the technology. Yes, we're winning. Oh, no. Right, some of this will be a slight revision of Yves Bonnet's presentation yesterday, so you'll have to bear with me if you all know about laboratory processes. Medication and doping control is generally a two-stage process, screening and confirmation. Screening protocol is designed to detect as many substances as quickly as possible, and typically labs these days analyze for over 1,000 different substances. The idea there is to report negative substances very quickly and cost effectively. However, if any of those screening tests indicate the presence of a prohibited substance, then we do more testing. We do not report on the basis of the first analysis. We then go on to perform confirmatory analysis, again as Yves mentioned yesterday. That confirmatory analysis is designed to identify the drug based on its molecular structure, and to do that on the basis of unique information for each substance. And we'll talk a bit about those now. I'm indebted to Ken yesterday as well for reminding us that whenever we do an experiment to collect data, we need to know what the question is we're asking. And confirmatory analysis is no different. You've often heard, I guess, qualitative and quantitative bandied around as two terms, and I'll go into some detail, I hope, to help explain the difference between those and why the cost differs. In qualitative analysis, the question we're trying to answer is the substance present? We're not interested in a threshold, and the majority of substances that are banned in sport, that are prohibited or controlled, whether by WADA, whether by the FEI, whether by the IFHA or the ARCI, are qualitative in nature. There is no threshold, so we are merely obliged to demonstrate their presence. In quantitative analysis, the question we're asking is how much is there? And again, this tends to apply only to regulatory substances, of which there are relatively few in sport. They tend to be divided into two categories. They're either endogenous compounds, made naturally by the body, and examples here are testosterone or hydrocortisone, or the substances which are generally considered to be in the environment of the horse through, let's call it contamination of feed or the environment, and that tends to be, typical examples are theobromine, and I'll include salicylic acid in this context rather than as a painkiller, because originally the threshold was developed due to its prevalence in many plant materials. It's only fair and appropriate here as well to acknowledge that in North America, they've also applied thresholds to a limited number of medications, as we heard on a number of occasions, and it's worked successfully for them as well. So, qualitative confirmatory analysis. There are international agreements defining the laboratory experiment that we need to carry out to determine whether a substance is present. And the Association of Official Racing Chemists, the AORC, is the body of professional scientists involved in horse racing, and we get together with WADA and basically come up with the same set of principles, so we harmonise across both human and animal sports testing. And this protocol meets the ISO 17025 requirement. ISO 17025 is the international standard that governs good practice in laboratories, in testing laboratories. This involves qualitative analysis, the concurrent analysis of a blank sample, a negative control, at least one, either a reagent blank and or a matrix blank, the matrix blank being a blank sample of urine or blood, depending on the test sample under investigation. It obviously involves the test sample itself, and it involves a reference material of the drug we think is present, so a standard, a positive control, if you will. The test sample data is compared to the reference sample data, and the gold standard is chromatographic separation and mass spectrometric identification. Again, we're going to revisit some of the things that Eve showed you yesterday. It's a revision for you all. There will not be an exam at the end of it, but this is the sort of thing you're getting. This is matching chromatographic separation. I'll risk the pointer. This is the blank sample. Actually, we should probably start with the reference sample. We've got a signal at 2.9 minutes. This is a time axis. So at 2.9 minutes, we have a signal in the reference standard. We have an equivalent signal in the same place in the test sample, and we have no signal in the blank sample. This is good. What we then do is look at the, eventually, we look at the mass spectrometric information. These patterns, we chemists get very excited about this sort of thing. This pattern of numbers is derived from the way the atoms in an individual molecule are put together. And the pattern of numbers and the actual numbers are unique for a particular molecular structure, i.e. a particular drug. So in this case, I'm sure you can see, this is the reference material. This is actual data from a real positive case. The reference material gives you this pattern of numbers. The test sample gives you a virtually identical pattern of numbers. We are therefore confident enough to report the presence of this substance. Skip that one again. I'm happy with 250,000 euros worth of mass spectrometer, and I can't operate. There we are. A simple remote. So there are internationally accepted confirmatory principles, as I said, for both the experiment and for data matching to make sure that those data between reference material and test sample are matched. And again, there's a good deal of equivalence between AORC and WADA. It's effectively a self-validating experiment. And on the basis of analysing 3 or 4 samples, we can give you a conclusion that says whether a substance is present or not. It's not designed to tell you how much is there. So again, because it's self-validating, because it's generic principles, we can apply this to any drug, even if we've never seen it before. If we can get hold of a reference standard, we can carry out this experiment on a live case. Quantitative analysis is different. Right, again, there are international agreements governing the sort of lab experiment we need to carry out in a regulatory environment to measure how much of a substance is present. Once again, same kind of correlations, AORC, WADA, ISO 17025, all those standards need to be met. And typically, the requirements for a quantitative test method are more complicated. Each lab must characterize a number of elements of the test that we're going to apply. This is what we call validation. And these characteristics include things like the range and linearity. What sort of range do we want? What sort of range of concentrations do we want to be able to detect and report? We need to work out the limit of quantitation. WADA typically has a recommendation written in its international standard that says the limit of quantitation must be at least half of the threshold. We need to work out how far beyond the threshold we need to be able to quantitate. How far does our calibration line go? And again, WADA tends to recommend at least twice the threshold. We need to find out how accurate our method is. How close to the true value can we get using this method time after time? The most important thing, perhaps, is the repeatability and robustness. Repeatability is known by a number of terms: variation, precision, the one I don't like, uncertainty. But it's basically how well can we repeat the experiment. And for this, we carry out the experiment on a number of different times with different operators, different reagents, different instruments. Carryover is interesting. We need to understand if you have a high concentration of a sample followed by a low concentration of a sample, does it have an effect? How can we control that effect? Matrix interference. We want to know whether the test we design will work in a wide variety of different individual blood samples or urine samples. It's no good method developing on 2, 3, 4 urine samples when you're likely to be analysing thousands of urine samples. So we need to investigate as many different samples as possible so we're absolutely confident that there's no interference from the matrix. And some independent quality control is also essential for quantitative analysis. All this means that this is an ISO 17025 requirement that the lab must do before deployment in a regulatory sense. So unlike qualitative, we can't do it on the fly. We tend to have to characterize the assay before we want to use it. Again, this means defining the dose response, the calibration range, choosing what we call an internal standard very often, which helps to control the variation in individual samples. I'll show you a little bit of data to show what that does. We analyze a range of different fortified calibration standards. We do it in replicate analysis. We usually do it at least in duplicate, could be triplicate, again, to increase our certainty in the result. Analyze a lot of negative samples, so we understand what the matrix interference might or might not be. Hopefully there isn't any. And then we need to assess the method variation. Again, I go back to, we carry out a complete experiment, maybe in an ideal world, at least 20 times, and on a number of occasions. So we understand that variability. So a typical quantitative analysis might include 6 different calibration standards to define the range at which we're testing, at least at 0, half the threshold level itself, and twice the threshold, say. Tendency to use at least 2 quality control samples. Again, at least one of those, independently from the calibration sample, should be at the threshold, so we understand the variability at the threshold, because that's the most important point. Obviously, the test sample needs to be analysed. A negative matrix control is often included. Could be the 0 standard from the calibration line, but very often is not. It's an independent negative control. And again, do a replicate analysis, do every sample at least in duplicate. What we're talking about here is perhaps 20 samples analysed to provide one result, unlike the previous qualitative analysis where we just do 3 or 4. I'm sure you're already beginning to get the idea of why it's more expensive. There we are. This is, again, some real data. Don't worry too much. This is an analysis sequence from a real quantitative analysis for testosterone in a urine sample. So this is the number of samples that are analysed just to come up with the results for one urine sample. So there's about 30 samples being analysed here. Slightly more complicated than usual, but nevertheless gives you some idea. This is the sort of data. I can't avoid the science. I'm afraid I'm a scientist. I get excited by this sort of stuff. So like Eve, I'm going to show you the odd signal. This is the mass spectrometry response for testosterone, the analyte under question. So we're looking at the retention time of 12 minutes, and we're looking at the response of this particular signal. What we also do for every single sample is look at an internal standard, and in this case what we're doing is correcting for individual sample variability through the whole process, through the extraction process, the analytical process. In this case, the internal standard is a molecule that's very similar to testosterone. It's a deuterated version of testosterone. What that means is that we take testosterone and we replace 3 of the hydrogen atoms with 3 deuterium atoms. This is heavy hydrogen. This means it behaves exactly the same as testosterone, but is a different molecule in mass spectrometric terms. So again, we measure the response of this internal marker. We add the same amount of internal standard to every single sample. And what we do is we calculate a ratio of the testosterone signal to the internal standard signal in every single sample. Okay, again, as I just said, we calculate the response ratio of testosterone signal to internal standard signal. We plot the ratio for every single calibration sample to define the dose-response curve. We then assign acceptability criteria to that curve during validation, so that when we deploy it later on, we know whether the curve has worked or not. That includes things like assessing the linearity. Again, something called the R-squared value is often quoted. We assess the allowability of how much replicate variation we can have, and the response range, the slope of the calibration line. All of this needs to be determined during method validation. Same for the control sample values. We calculate the repeatability of those control sample values. How much variation are we going to allow once we start using this in anger, as it were. Calculate test sample values by comparison with the calibration curve, and also assess that blank and negative population background. Again, all this is done during method validation. Again, what that looks like, we'll go back to this table of sequence. What you have here is, this is the area of the testosterone analysis. So this is the response to the testosterone signal. This is the response of the internal standard signal. This is the calculated ratio of those two signals. This is the calculated amount, and this is the variability between the duplicates of each sample. So all this data must be characterized and recorded. Skip the slide. What does that look like? I'm sure you've all seen these calibration graphs. The end line is, this is our calibration line It's a dose-response curve, strictly speaking. In this case, it's a straight line. We have an R-squared value of 0.9992, which in analytical terms is very good. It's very acceptable. We have a nice linear response. The concentration of testosterone is shown on what we call the x-axis on the bottom here. So the range runs from 0 to 200 nanograms per mil. We are confident we have a good understanding of the response of testosterone in that range. So again, this is a good curve to use. There we go. The analysis that you just saw, the calibration line meets all the acceptability criteria. The QC samples that we analysed, again, this is real data, it's a real test. We have 3 different quality control samples. We have a low value applicable for the gelding in international horse racing. We have thresholds for testosterone in geldings and a different threshold for testosterone in fillies. So we have a control at the gelding threshold, nominally at 20 nanograms per mil. In this particular case, we analysed 2 portions of sample. We got results of 19.9 and 19.6. That's within the acceptability range that we allow from the assay characterisation. The control for filly, the nominal value is 55. We've got values of 53.9 and 60.3. They are again within our acceptability range. And the high control, just to see about the high levels, has a nominal value of 150, and we've got answers of 155 and 151. Again, these are within our acceptability ranges. The blank samples both measure 0, which is good news from the analyst perspective anyway. And the sample itself has 2 values, 113.2 and 113.5. So the mean at 113.7 is fine. The replication is within a 1% variability. That's acceptable. And it's well above the threshold, which includes the method variation. So effectively, we will only report a result if the sample concentration exceeds the threshold. This was in a filly, in a female horse, at 55, plus the maximum variation we think the assay delivers under experimental conditions, which is another 12. So in other words, there's a fair degree of benefit of the doubt going to the trainer there. Unless, if the results, for example, if the results were 68 and 60, we wouldn't report it as positive because both results do not exceed our variability as well as the threshold. But in this case, as you can see, 113 is well in excess of 55, so we're comfortable reporting that. Sorry, can we go back? Skip the last couple of slides, can we? One more. There we go. Right, money. I'm going to introduce an accounting term. First speaker to do so. These are my estimates of the costs, and these are fully absorbed costs, not marginal costs. Typically, and I guess acknowledging what Kent and Steve Schumacher have been saying, these are costs of change for laboratories that are not already operating these thresholds. And these are the upfront costs. Kent referred to them yesterday. These costs have already been incurred by the USEF lab. They've done all this work. It's not that they haven't, but they've already done it. They've been operating them for some time. My estimate is something like 20,000 euros to validate an individual threshold in an individual matrix. That's because we go back to, we're going to repeat the experiment 20 times. It's going to take us maybe 50 days. We're going to find 50 analyst days to do that with equipment time with people to assess that variability I talked about earlier on. And that would change for a different threshold in blood, a different threshold in urine. So USEF actually would have a cost of change if the threshold proposed were adopted and were different to the one they're currently operating on. So there is a cost of change regardless in validating those assays. But that's a one-off upfront cost once we get going. Once we get going, the individual costs are not as bad. There is a cost implication. Quantitative analysis is more expensive than qualitative analysis. Again, I hope you can see that, analysing maybe 15, 20 samples to give you a result as opposed to 3 or 4. We also still have to do a qualitative confirmatory analysis for quantitative analyses. We still have to identify the substances present. And then we have to answer the question, how much is there? So it's still an awful lot of work, and typically, I guess, around €1,000 would not be an unrealistic cost, and say about twice as much as a qualitative analysis. Finally, literally, I guess there are a few more add-on costs that you might want to consider if we're just strictly talking costs here. It will take more time to complete the testing. It is more complicated. We will probably have to look at process changes to deal with potential risk of carryover. If we suddenly start having samples with 10, 12, 15 micrograms per mil of phenylbutazone knocking about in the system, whereas currently we're talking about nanogram per mil, then we will have to look at our processes differently. There will also inevitably be some legal costs perhaps in challenges. The problem with putting numbers in a regulatory environment is that people tend to challenge you on those numbers. Do you mean 113.5 or do you mean 114.5? When you do the B sample analysis, one thing I guarantee is the B sample will give you a different number to the A sample. I'd be stunned if it didn't. You'd expect variability, especially if it's done in another laboratory. The legal costs are likely to be more complicated in challenges to quantitative analysis. I'm not saying we shouldn't do it, I'm just alerting people to the potential for costs. And one thing that Eve mentioned in brief yesterday, if we're talking about phenylbutazone in particular, we do know that phenylbutazone in blood samples is not always as stable as we'd like it to be. I suspect that plasma esterases cause some deterioration of phenylbutazone, and in some samples it degrades. So you've got to be prepared for when you do the B sample, you may get quite significantly different results. That is my lot. So thank you, second.